Okay, so we are now moving into section 6.6, applications to physics and engineering. How many of you have to perhaps take a physics or engineering course in the future, or maybe you're taking one now, like Physics 1 or something like that? Is anybody in that category here? Okay, Mario's currently there and Ange is there. Okay, all right. And Joseph, all right, wonderful, wonderful. Well, one of the concepts that's very important in, okay, Sandia, next semester maybe physics. Okay, no problem. Well, let's review a few kind of basic concepts that you would have probably seen. You don't have to take a physics class to have seen these, but one of them is Newton's second law of motion. Okay, Newton, hold on, let me get it up here. So normally in calculus, like if you took calculus 1, how many remember that the position of a particle, we would denote that position by the letter S? That's sort of common, like S of t. The particle moves with respect to time, and S of t is the function that models the position of the particle. Is that something you recall from calculus 1? Okay, Taj remembers that. And Newton's second law of motion says that force equals mass times acceleration. Okay, so hopefully you have heard of that. And the derivative of position is equal to velocity. So ds dt is equal to velocity. But then the derivative of velocity is equal, that's right, Sandia, the derivative of velocity is equal to acceleration. So the second derivative of position s of t with respect to time is equal to acceleration with respect to time. And so you see here, this is section 6.6, force equals mass times acceleration. Okay. And okay, well, good, Sandia. Yeah, and calculus 1, hopefully Newton's law came up there as well. And there's some other concepts too. Well, I'll mention, this is important. So force, there's different ways to measure force. Okay, so one way is newtons. How many have heard of newtons before? Newtons is equal to kilogram times meters divided by seconds squared. Okay, so David, Taj, Mario, and Jan and D'Angelo heard of that. Wonderful. So the force of 1 Newton acting on a mass of 1 kilogram produces an acceleration of 1 meters per second squared. Okay, so that's the metric units. All right, very good. Excellent, Sandia. And then another unit of force is the pound. Okay, that's the US customary system. So if you weigh 150 pounds, that's the amount of force that it would take to move you. Okay, so pounds are units of force. And we are interested definitely here in section 6.6 in computing work. So work is equal to force times distance. How many recall that definition? Work equals force times distance. Okay, good, good. High school, Taj remembers that. Mario, Nathaniel remembers that, and Ange. And sure, so you haven't done any work on an object unless the object moves, right? So if you apply a force to an object, some constant force, and then the object moves a certain distance, you've done a certain amount of work on the object. Okay, like pushing a table or pulling a wagon, that sort of thing. And they mention here that if force is measured in newtons and distance in meters, then the unit for work is Newton meter, which is called joules. This is in section 6.6. And then if force is measured in pounds and distance is in feet, then the unit for work is the foot pounds. Okay, the foot pounds. So they give a couple of examples here where they compute work. Joules, that's right, Sandy. It comes up. It comes up in physics and chemistry. Absolutely. If you were to lift a one, so like, I mean, I have things highlighted. But I can re-highlight here. I'll put this in. I mean, this is where we're at right here. So if you lift a 1.2 kilogram book off the floor to put it on a desk that is 0.7 millimeters high, the force you exert is going to be 1.2 times 9.8. That's 11.76 newtons. Okay, that's 11.6 newtons. And then the work that you would do would be equal to the force times the distance. Okay, and so that force times distance is just the 11.6 newtons times the 0.7 meters. That gets you 8.2 joules. Now, incidentally, above, where does that 9.8 come from? They have force equals mass times g. And then g is 9.8. Okay, that's gravity. That's good, Tosh. Good, Mario. That's acceleration due to gravity. Okay, so, you know, in section 6.6, the type of problems you're going to see, you know, you'll be dealing with problems where you're going to have the metric units, and then you're going to have to be dealing with problems with where you have the customary US units. Now, if you were to, for instance, hold on here, let me just highlight this, put this in light blue. Okay, so if you were to take a 20-pound weight and lift it 6 feet off the ground, force is the 20 pounds. So the work done is force times distance. That's 20 pounds times 6 feet. That's 120 foot-pounds. So when you're dealing with, when your force is in pounds, gravity is not involved. You don't have acceleration due to gravity. You don't need that because the force, the pounds is already in pounds is already a unit of force. Okay, so are there any questions so far on these two ideas? Okay, well let's proceed on. So, right, Sandia, you're good. You're good. Okay, good, good. So now this definition where work equals force times distance, that's a very fundamental definition, but that's where you have a constant force. What we want to do in section 6.6 is we want to modify the work so that the force applied to an object could be a variable force. Okay, so for instance, let me just bring up the blackboard here, or the whiteboard, I should say. So like, for example, if you have a X here, okay, and okay, you have a function f of x. Let's say this is your force function. Well, the force varies, and let's say you're going from A to B. So the force varies. It's a variable force, and it changes with respect to x. Different values of x mean the force changes. Okay, so if, for instance, you're pushing an object and you don't push the object at a constant force, but you change your force, how, you know, you're changing the amount you're pushing at different values for different values of x. In other words, when the object is at, I want to say this the right way, I want to say it the right way, different, like maybe A is, you know, 2 feet. So I want to say this the right way. So you're pushing this object, and the object starts off at 2 feet away from the origin. And then, you push the object, and maybe at x equals 1, you're 3 feet away from the origin, okay? But between x equals 2 and 3, your force is varying. Your force is varying. So you're doing work on the object because you're moving the object from point A to point B, but the force is variable. So the question is then, how do you find the work that you did? How do you find the work you did? Let's go back to the book and see how they do this. So, okay, what they do is they say, all right, we're gonna have our force function, and maybe what I'll do, let me just, there's quite a bit highlighted there, quite a bit highlighted. Let's see if we can unhighlight a few things here. Okay, so what we're going to do is like I said, we're going to suppose an object moves along, let's say, the x-axis in the positive direction from x equals A to x equals B, and at each point between A and B, there's a force that acts on the object. Okay, what we can do is what we've done similarly in the previous sections. We can take that interval from A to B, and we can divide it up into subintervals. Okay, we can divide it up into subintervals. We divide the interval into subintervals, and for each subinterval, we'll choose a point in the subinterval, and then we'll compute the force at that point. So you'll have f of x sub I star. All right, if n is large, then delta x is small. So over the subinterval, the force doesn't change too much over that particular subinterval. So what would the work be? What would the work be over the subinterval? The work on the ith subinterval would be equal to, hold on, the work on the ith subinterval would be equal to the force times over that subinterval, which is approximately the force evaluated at x sub I, which is a point on that little tiny subinterval. We take the force and multiply it by delta x, which is the distance that the object moved on that subinterval. Okay, so this w sub I is the work done in moving the particle along one subinterval. Okay, you see how they say you're moving the particle from x sub I to x sub I minus 1 to x sub I. Well, that means then that that's a distance of delta x. So the work that you're applying is approximately equal to the force over that subinterval times delta x. Now there's a typo here. It should be a lowercase f. They have a capital F. But then, are there any questions on that? How the work over the ith subinterval, w sub I, is approximately equal to the force over the ith subinterval, f of x sub I, times delta x, which is the distance of the subinterval. Are we okay on that? Give me a thumbs up if you're good. A few thumbs ups if you're good. Okay, Taj is good. And Ange is good. Wonderful, wonderful. Okay, well, that's fine. That's fine. All right, so the work is going to vary from subinterval to subinterval. So if we wanted to find the total work, what would we do? Well, we would just add up all the little work values, all the w sub i's, and then add them up. So we get a Riemann sum. The approximation will get better if we make n larger, of course. So if we let n get large, what's going to happen to this summation, to this Riemann sum? What does it become if we let n get large? what would it equal? What's a Riemann sum become as you take more and more subintervals? What is a Riemann sum? It turns into an integral. That's right, Taj. That's right, Ange. And then you get the work. So you see the work, then if you have a function, a force function that varies with respect to x, the work is just the integral of the force function. How about that? So now, because you know calculus, you can do work problems where the force function is variable. So that's going to open up a variety of problems, a variety of more problems you can do. Are there any questions on this? I think we'll continue in the book here and look at they have some good examples here, examples 1, 2, and 3. I think we'll look in the book. All right, let me know if you have any questions. Okay, well then let's proceed on here. Let's proceed on. So, okay, we want to keep moving through the book here. Okay, so the first example says when a particle is located a distance x feet from the origin, let's suppose a force of x cubed plus 2 or x squared plus 2x acts on it. And I've highlighted some key parts of the problem, okay? How much work is done in moving this particle from x equals 1 feet to x equals 3 feet? The solution is to just take the integral of your force function from limits 1 to 3, and you will get 50/3. So the work done is 16 2/3 foot-pounds. That's your work done. Are there any questions on that? All right, pretty straightforward here. Let's continue on. How many have heard of Hooke's law? Hooke's law. Okay, Ange? Well, Hooke's law states the following, that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. Okay, so Hooke's law, Sandia, I'm not sure if we covered that in Calc 1 or not, honestly. I teach Calculus 1. It's been, I mean, I'm actually teaching it again this semester. It's been a little while. I don't recall teaching it in Calculus 1, but it is possible. But what it says is the force required to maintain a spring stretched x units beyond its natural length is proportional to x. Okay, so how many physics 1? Okay, Ange, thank you. So how many have like taken, notice if you take a rubber band and the more you stretch the rubber band, the more the rubber band wants to like pull your fingers together. How many have noticed that? Sure, and you know, you have to maintain a greater force to keep the rubber band stretched the more you stretch it, right? Well, that's what Hooke's law is like, right? It's the force is proportional to the distance x that the spring or rubber band is stretched. So force is equal to k times x. Okay, so and k is a positive constant called the spring constant. The spring constant depends on the type spring you're using. Okay, and it says Hooke's law holds provided that x is not too large. Okay, so let's look at an example. Well, here is Hooke's law. I mean, we talked about it, but there's a picture. And this is something, if you take differential equations, Math 282, that you'll be dealing with a lot. And of course, it comes up in physics as well. But you know, the natural position of a spring or a rubber band would be when the spring is not stretched or contracted. But in B there, they show you the stretch position of a spring, and the force is equal to K times X. The more you stretch the spring, the greater force you need to keep the spring stretched, because what's the spring want to do? It wants to do what's called a restoring force. It wants to, if the spring is stretched, it wants to contract if you let it go, and you got to use force to keep the spring stretched. And the more you stretch the spring, the greater the force you need. Okay, so Hooke's law, let's look at an example there. So example 2 says a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? Okay, how much work is done? So, okay, according to Hooke's law, we'll look at the solution now. According to Hooke's law, the force required to hold the spring stretched X meters beyond its natural length is equal to K times X. Okay, when the spring is stretched from 10 centimeters to 15 centimeters, the amount stretched is equal to 5 centimeters, but we're going to convert centimeters into meters. Okay, we're going to convert. Let me see. I can maybe highlight that. Sorry, let me just try. Highlighting is sometimes a little tricky. Yeah, you gotta convert the 5 centimeters into 0.5 meters, right? You have to do that because with work, you want your units to be in meters, okay, for the metric units. So what we have to do, we need to determine the value of our force function F, but we don't know what K is. We got to find out what that spring constant is. Well, we know that when the spring is stretched 0.05 meters, then that requires, hold on here, that requires a force of 40 newtons. So that means that F of 0.05, hold on, F of 0.05 is equal to 40. And so we can solve for that K constant, that spring constant. So K will equal 40 divided by 0.05, which is 800. It is 800. It's not coming up exactly like, you know, I have the box highlighted, but maybe, let me just see if I can do it. Sometimes you just have to, yeah, K is equal to 800. So now our force is equal to, I want to highlight this. Yeah, our force function is equal to 800x. Okay, and so now we can compute the work. And obviously, let me just see here, hold on. Hold on, everybody, let me just, if I can highlight it, that's really what I want to do. Good, there, that works. There we go. So the work is equal to the integral from, well, the force is 800x now, and so the work is equal to the integral from 0.05 meters to 0.08 meters, okay, of 800x dx. So when the spring starts off at 15 centimeters, that's equal to 0.05 meters. And then it's stretched to, it's stretched to 18 centimeters. Well, that's equal to I'm sorry, I didn't say that right. Yeah, the spring starts off being stretched at 5 centimeters beyond its natural length. So that's 0.05 meters beyond its natural length. And then the spring is stretched then up to 18 centimeters beyond its, I'm sorry, 18 centimeters, but 18 centimeters is 8 centimeters beyond its natural length. So that's 0.08 meters beyond its natural length. And that's why your limits are from 0.05 to 0.08. And when you integrate it, you get 1.56 joules. Okay, are there any questions on that? Any questions on that? On this second example, how they work it? Please let me know. Give me a thumbs up if you're good. Give me a thumbs up if you're okay. If you're comfortable. Okay, Ange is comfortable. Thank you, Taj. Thank you, D'Angelo. Okay, okay, well, very good, very good. So let us proceed on then. Let us proceed on to the third example. Now, what I want to do, look at the example here, and give me just one moment. One moment. Okay, thank you. I'm back. So work needed to lift a cable. So in example 3, we have a cable that's a 200-pound cable that's 100 feet long. Okay, and it hangs vertically from the top of a tall building. And they're asking you how much work is required to lift the cable to the top of the building. Okay, how much work is required to lift the cable to the top of the building? So pictorially here, here's our picture. Okay, there's our picture. Okay, and what's going on here? What's going on with this picture? What are they doing? Well, so I want to say this the right way. I want to say it the right way. The 100 there, the axis they're using, they're calling it the x-axis in figure 2. And normally, you know, the vertical axis is a y-axis, right? But they're just calling this the x-axis. And they have there from 0 to 100 because the cable's 100 feet long. And then what they do is they go along the cable and they pick a value along the cable, x sub I. And then they look at a piece of the cable in the picture there. The cable's hanging from the building, and that piece of the cable is called delta x. Okay, so let me sort of give you a little bit of a perspective here, a little more perspective on this. Hold on here. No, I want the line. So this is supporting example 3 from section 6.6. Okay, here's the cable. The cable is 100 feet. So 100 foot of cable, 100 feet, okay? Now, I'm gonna look at two pieces of cable, and each piece of cable has a width of delta x feet, okay? So I think I'll write that in there. Delta x feet, okay? And what I can do also, let me just make sure I'm doing this. I'm gonna put this here. And this is, of course, the top of the building. Top of the building. And again, you have 100 feet of cable. Okay, here's a piece of cable. I'm going to call that piece of cable cable 1. Here's another piece of cable. I'm going to call that piece of cable I'm sorry. So I have the small, tiny piece of cable, cable 1, I mean piece 1. And then the second piece of cable, I'll call piece 2. So 2 pieces of cable, piece 1 and piece 2. Which is going to take more work? Which is, and I'll even add this to it. I'll even add this to it in the picture. So I'm going to say this right. Let me just see here. I'm going to call this x sub 2 star. So that's the distance that the second piece of cable is from the top of the building. And then the first piece of cable is a distance x1 star. So it's further down from the top of the building. My question is, which piece of cable, well, is it going to take an equal amount of work to move the first piece of cable up to the top of the building as the amount of work needed to move the second piece of cable up to the top of the building? Does the first piece of cable, to move that to the top of the building, would that require the same work as to move the second piece of cable up to the top of the building? What do you think? Well, actually, so I appreciate both responses. And Taj, you're right. You're right. So hold that thought, Ange. The second piece of cable, oh, I'm sorry, the piece number 1 is going to take more work, because you see both pieces of cable are delta x feet long. So they weigh the same. Both pieces of cable weigh the same. Now, how much do they weigh? Well, if you take delta x, I want to say this the right way. If you take delta x feet of cable, okay, if you take delta x feet of cable and you multiply that by the weight of the cable's 200 pounds and it's 100 feet long, which means the cable weighs 2 pounds per 1 foot. So you see, if you take a piece of cable with a width of delta x feet, and then multiply it by 2 pounds per foot, the feet simplify out. The feet here simplify out, and you're left with 2 delta X pounds. So both cable 1 and both the first piece of cable and the second piece of cable weigh the same amount, but the first piece of cable, you're having to lift that piece to move the entire cable to the top of the building. You have to move every little piece of that cable to the top of the building. The first piece of cable is down lower. It's down low, further away from the top of the building. So it's going to take more work to lift that first piece of cable to the top of the building than the second piece of cable to the top of the building. Do you see that, Ange? Do you see that? Are there any questions on that before I go to the solution here? Okay, all right, good. So if we then go to the book, how would we find the work needed to lift the entire cable, the entire 100 feet of cable to the top of the building? Well, what we would need to do is we'd say, okay, and this is something I mentioned right there on the whiteboard. Every little piece of cable, and we're taking the entire cable and breaking it up into a bunch of little pieces of cable. Every little piece of cable will weigh. Will weigh. I'm not saying this right. Hold on. That isn't what I want yet. The weight of the ith part of the cable is 2 times delta X pounds. But the work then to bring that piece of cable up to the top is going to equal 2 times delta X pounds times the distance of xi feet. So to find the weight, to find the work needed to bring the entire 100 feet of cable to the top of the building, to get that total, hold on here, let me just highlight it. Okay, to get the total work, sorry, I don't know why it's doing this, stop that. Let me remove the highlight. It keeps wanting to, all right, I'll just leave it this way. To find out the entire work needed to lift that 100 feet of cable to the top of the building, you add up all the little pieces of work to bring up each little piece of cable to the top of the building. And it turns out then that the amount of work is 10,000 foot-pounds. So isn't that amazing what you just learned here? You're with knowing calculus, you're able to do a problem like this. Okay, how many think that's really absolutely amazing? This third example. Okay, Taj is liking it. Mario's liking it. Excellent, excellent. Well, these are just some examples from section 6.5, the work section, and or 6.6, sorry, the applications to physics and engineering. And we're looking at work. We're going to focus on work and a lot. We're going to be next week now, on Tuesday's class, we're going to be continuing section 6.6. And we're going to be looking at some other applications. We're going to be talking about how much work it takes to pump water out of a tank and some other applications. So if there are any questions, if there are no questions, I will stop the recording. Okay, I'll stop the recording here.